In the last set of videos, you're focusing more on sound waves. Now we're going to start focusing a little bit more on light waves. Now you guys have done some stuff with light, with like refraction and some basic quantities and the V equals F lambda expression and stuff like that. We're going to start focusing a little more on the nature of light and a few of the cool things that come out of looking at light. Now, first of all, studying light is it's actually really hard to actually study light. For a couple of reasons. First of all, because it is so unbelievably fast. There is nothing faster. It is unbelievably difficult to study because one of the reasons is because it's so incredibly fast. But probably even one of the trickier things, because we can slow light down by using materials with indexes of refraction that are really high and stuff like that. They can slow light down to really slow. With really high index of refraction type materials. But one of the other reasons that makes light unbelievably difficult to study is when you actually interact with it. When you interact with it or study it, basically it no longer exists. You study it, like you watch light hit something and hit your eye. And well, when you actually observe light or when you actually study it, no longer exists. Because even if you're going to like watch light, well, the only time you actually see the light is when it actually hits your eye. And if it hits your eye, then it doesn't exist as light anymore. It's changed into energy that's gone into the optic nerve, into the brain, it's been processed by the brain. So it's kind of hard because light is one of those things, one of those very few things out there that you never actually are able to study it in its actually, like its true form. Like if you're going to study a car and how a car moves, you can actually watch the car and the car still exists. But light doesn't exist once you actually observe it. So when you interact it or you study it, it no longer exists once it has actually been observed. It's hit something. It's changed into other stuff. So that's one of the biggest reasons by far that makes light really hard to study. But people have been working on it for thousands of years. And one of the cool things is the more you study about light, the more strange things you actually learn about. It's really neat what light can actually lead to. Okay, now we're going to start by looking at this in terms of some of the main theories that were done. There's been a few theories of how light works and all that kind of stuff, but we are going to focus on one of the first major theories that was published, and that was published by Newton. And Newton published a document called Optics, which was trying to explain how light works and how light does the things that it does. And Newton's theory is actually called the Corpuscular theory of light, and it's basically a particle theory of light. And the basic premise behind Newton's particle, got a little extra in there, Newton's particle idea of light is it sort of acts like little tiny bullets. So light was basically like little bullets flying around. Now, of course, you have to be able to explain how light does some things that it does. So let's look at some of the basic things that light does in different scenarios. For example, light will reflect. So he said basically they just, they bounce off. I mean, that's pretty simple. You shoot bullets something hard, they're going to bounce off, ricochet off. So that was really simple. Okay. Light, of course, also refracts. And how do you explain refraction? Well, he got part of it right. What he said was that the speed changes. That part he got right. But the problem is he actually had it reversed. And I'm just going to try and draw something here to explain the basic idea. Suppose you've got a platform, big flat platform, and on the side of the platform there's like a ramp that goes off the side. So maybe something like this. And you take a marble or something like that, and let's go with a red marble. You take a red marble and you roll it across the top of the flat part. And as it goes across the top of the flat part, it's going to go nice and straight. But then when you hit this boundary, this ramp part, it is going to speed up. And as it speeds up, let's draw a line. As it speeds up, going down the ramp, it's going to change its direction, which is literally what light does. And same thing for all the colors. And blue will actually do the same type of thing, and the blue would come along, and blue actually will bend even more. Okay, and then you have all the other colors in between. You got the green, you got the orange, you got the yellow is in there. Without the yellow in there, yellow will be right about there. All the different colors. Okay, so he said that the speeds change, but he actually had it reversed, because if this was air per se, so let's say this was air and this was water, this is what it would basically look like. He has it reversed. He had it said it would speed up when it goes into water, when it actually slows down. So he had the idea right where, when the light hits a different medium, it changes its speed, which would change its direction, just like a marble would go here and then speed up and change direction down the ramp. Right idea, but he had it reversed. Okay. Now, this leads to something else that light does, and that is light will disperse. And this is when you have like a prism, you use a prism or something like that to make colors, which is actually a modification of refraction. And that's what you get here. You have different colors would actually spread out. And he basically said the reason why red goes straightest is because it's the fastest. So the red's the fastest one, and it goes straighter, while blue is slower, so the ramp has a larger effect. So all the different colors had different speeds. So dispersion is just a modification of refraction. And he said prisms and stuff that can make the colors, because each color had its own speed. So that whole ramp idea then has more or less of effect on it depending on the speed, which has its own color. So you could explain how you get rainbows and stuff like that. Okay. Now there's also diffraction. And of course, diffraction is when things go through openings and they spread apart, like waves will go through openings and spread apart and stuff like that. Well, typically light goes straight. There's very, very, very little diffraction for light. It goes pretty much straight. It's actually what's called rectangular propagation. So when light goes through an opening, like when light goes through a doorway from a bright room to like a dark hallway or something like that, it makes the shape basically of a rectangle on the floor. Like it goes pretty much straight. It propagates in the shape of a rectangle. So you get very, very, very little bit of diffraction. But he did say, it'll spread out a little bit. Light will spread out a little bit. So he said you get a little spread from collisions at the opening. So you do get a little bit of diffraction occurring, and that's because some of the bolts are like hitting the edge of the opening, and since they hit the edge of the opening, they'll ricochet a little bit and cause a little bit of diffraction. So light goes pretty much straight, and you get a little bit from some collisions at the opening, and that's about it. Okay. Now, one of the other things that kicks in is some problems that he had, and there was a couple problems, but one of the things that he had trouble explaining was partial reflection. Okay. Like when stuff hits barriers, when light hits barriers, even when we go back to that simulation that we did with refraction, when light hit the barrier, some would reflect, some would refract. There's always partial reflection. He couldn't really explain, or had trouble explaining partial reflection. Like, why would some of the bullets go through? Why do some bullets bounce off? That didn't really make much sense. He could explain pretty much everything else that was going on, the reflection, refraction, dispersion, diffraction, no problems explaining that type of stuff. But the partial reflection, that was hard for him to fully explain. So, like, why would some go through and some would reflect? Like, why do you get both? Why shouldn't it be one or the other? Okay, so these are some of the things that he was easily able to explain. He was a pretty smart guy when it comes to this type of stuff, but of course there was always problems. Now, one of the things about the bullet idea, and one of the things that they had, and I'm going to give myself a little more room here. I'm going to take this and I'm going to shrink this down, give myself a little bit more space here. One of the things, though, that they were curious about, though, is if this is actually a bullet. If light is a bullet, is there actually a speed? Now, that was one of the big things that they want to try and figure out. If, is it a bullet? Well, if it is actually a bullet, is there a speed for this bullet? Does it actually have a speed? Obviously, if there is a speed, it's really, really fast. So if it is a bullet, is there actually an actual speed for this thing? Or is it instantaneous? Okay, so does an actual speed actually exist? Or does it just instantly go from one place to another? And this is one of the big questions for light that lasts for a really, really long time. And lots of people tried to figure this out. And in the next video, we're going to look at some of the major experiments and major steps that were done in order to try and figure out this question right here, because that's a big one right there. Okay, so we'll start looking at that a little bit next.